All right, so chapter two, we're going to talk about measurements, and we're going to talk about all types of measurements, how to take measurements, how to record measurements. We will also cover in this chapter a lot of the fundamentals of chemistry and sort of doing calculations. We'll talk about scientific notation. We'll talk about significant figures. We will also get into what is known as dimensional analysis, problem solving, how to set up problems. In addition to being very strict on what they want you to kind of know in this class, they do also want you to be able to set up problems as you go continue on in your chemistry sort of 1A, 1B sort of section. They do want you to sort of set up problems a certain way, and that's what they typically will mean, and what we'll mean in this class as well when we say like show your work, right? So there's sort of a certain way to kind of show your work in chemistry. It is typically what's known as dimensional analysis, and we'll talk about that in this chapter as well. In addition, we will talk about density to sort of finish up the chapter, and I think we also hit some temperature conversions along the way. So a lot sort of stuffed here in chapter two. So let's get into it. So really the first really important thing about sort of measurements is units. And, you know, if I wrote something like 150, you know, what am I really talking about? And nobody would really know what I'm talking about because really that's just a number, right? There is no frame of reference for what that number represents. Could represent $150, which would be great. Could represent 150 pennies, still not too bad since they don't make pennies anymore. 150 apples, not bad. You can make some apple pies. But really, just the number by itself has no sort of reference to what it means, what it's representing. So, one of the first things you should definitely get in a habit of is not just lay up numbers. There should always be, when you take a measurement, a number and a unit. The unit, again, tells the person when they look at the number what it basically represents, and sort of what scale you're using for that particular measurement. So when we talk about units, there's really kind of two widely used systems of units. There's sort of the English system, or the US system is sometimes referred to, and that's the one that we use here typically in the US. Then pretty much everybody else in the world kind of rolls with the metric system. And those are the two sort of the main units that you come across. Again, sort of English or US units and metric units. And in 1960, there was a convention on weights and measures. Sounds like fun. And basically, what came out of that sort of convention or conference was this idea that, you know, as the world's sort of getting smaller, people are obviously doing business with each other and sort of communicating from different countries. You know, if somebody in the US is doing measurements, you know, in inches, and somebody in the Europe is maybe doing measurements in kilometers and centimeters, there's a big difference in those measurements, right? And it could lead to a lot of trouble, like especially if you're building things that need to be very, very precise, like on space shuttles, right? We got to get the right measurement there. And if you're using different units, then those are bad things. So what came out of that is what is sometimes referred to as the SI unit. The SI unit is sometimes referred to as the International System of Units. You oftentimes in chemistry will hear the SI unit for mass is this, or the SI unit for length is this. For all intents purposes, it's pretty much like the metric system, sort of one out of the two, and the SI unit is for that. Now, when we talk about units, it's also really important to understand that when you do see a unit, what is representing? What type of measurement is it representing? So the SI unit for mass is a kilogram. Other common sort of mass units that we come across, grams, kilograms, centigrams occasionally. Length is, the SI unit is meters. Time, the SI unit is seconds. And for temperature, this is one if you're not familiar with, you'll be very, very familiar with by the time we're done with this class, or if you continue to take chemistry classes. The SI unit for temperature is Kelvin. It used to be called the absolute temperature scale. It was later renamed for obviously a guy named Kelvin. And that is pretty much, I would say, in all your chemistry sort of classes that you take, the unit that temperature needs to be in. Yes, sir.
Kelvin to Celsius, but instead of starting at the freezing point of water, it starts at absolute zero.
Yeah, we're going to actually talk about that in a little bit in this chapter. Yep. And there is different sort of scales for both Kelvin and Celsius and stuff like that. But like I was saying, pretty much every chemistry formula that you come across, if you have anything that deals with temperature, Kelvin is typically the unit that you need to put it in. Even if you're asked to give the answer in Celsius, when you go into the formula, it's got to go into Kelvin. There's only one sort of formula that we will see in chapter 10, all of your chemistry career in terms of temperature, that we do leave it in Celsius. But for the most part, 99.9% of the time, that is a very, very important one. So you definitely should know, the sort of quantity that goes with this particular unit. You definitely want to make sure that you understand what that is so that when you come up and tell me that you just weighed out, 42 milliliters or something on the balance, the scale, yeah, I'll know that, that's not really correct because milliliters is a volume rather than obviously a mass. So you want to make sure that you understand that. Volume, common volume sort of units, maybe not SI units that we come across as we will see, liters and milliliters are very common sort of volume units that we do see as well. So let's talk about some of these mass and length and volume measurements and some of these that you, again, should probably know. I would say for sure the SI unit for length is a meter. That's a good little one to kind of know, the conversion between a meter and inches. 1 centimeter is equal to 0.01 meters. Are 1 times 10 to the minus 2 meters. This is this number in scientific notation. And we'll talk more about that. Whoops, notation. 1 decimeter is 0.1 of a meter, and 1 kilometer is 1,000 meters. I will say definitely probably all three of these sort of conversions are ones that they do expect you to know and will kind of pop up along the way. So those, again, are good ones to make sure that you do know sort of those conversions. These are prefixes, and these are prefixes that are used to change sort of metric sort of values, so you don't have a lot of zeros and stuff like that. And this chart here is also a good one to know. I think we'll see it a little bit later as well, but I'll just put no here as well. Mega, kilo, deci, centi, milli, micro, and nano. Those are all prefixes that you use a lot in chemistry. I would say in our class, for sure, kilo, deci, centi, milli, and nano does pop up. As you go through 1A, 1B, you will kind of hit these other ones a little bit more. You'll kind of see those a little bit more, the micro and the mega as well. This is the prefix. These are the symbols here to the left, and to the right of that is the meaning in more of a whole number, and also the meaning in scientific notation. And this is very commonly how you see these tables written, like 10 to the 6, 10 to the 3. And by the way, when you do see 10 to the 3, that is the same as 1 times 10 to the 3 in scientific notation, 1 times 10 to the 6 for the top one, and so forth. I will say most of the time people use these sort of prefixes to change the meaning of a number. They oftentimes will do that conversion backwards and will not do it correctly. So just to show you, and again, we'll see it a little bit later on as well. For example, if we took kilo and we see it's 10 to the 3, which once again is 1 times 10 to the 3. What that means is when you look at a prefix sort of like this, that 10 to the 3 is how many there are in the base unit to one of the prefix units. So what am I talking about? So what I'm talking about is if I had grams and kilograms, right? The base unit here for both of them is grams, right? They both have grams in common. Is really the base unit here. The kilogram is the prefix sort of unit here, right? This is really the prefix unit. So when we would do this, what that is basically saying is in one of the prefix units, there is 10 to the 3 grams. And it's very, very common that people will do it backwards and go in 1 gram, 10 to the 3 kilograms, and always kind of want to switch those guys backwards. So when you look at this chart here, this part of the table, that is how much there is in the base unit to one of those prefix units. It doesn't really matter what the base unit is. If I had a kiloliter and a liter, in 1 kiloliter, there would be 10 to the 3 liters. If I had 1 kilometer and meters, in 1 kilometer, there would be 10 to the 3 meters. So it really doesn't matter what the base unit is. The prefix works the same, but it is a super common error that people make. They always want to kind of flip it around the wrong way. And it works for this as well. For example, centi here. If I went to centi, centi here is 10 to the minus 2, which is basically that. And what that would mean in 1 centimeter, which is the prefix unit, there would be 10 to the minus 2 meters, or 1 times 10 to the minus 2. In 1 centigram, there would be 10 to the minus 2 grams. So it's really important to make sure that you sort of understand how to use those properly. Like I mentioned, it's a really, really common error that people make all the time, sort of flipping those the wrong way. Any questions on that? By the way, as we will also talk about later on in this chapter, what we are looking at here, either any of these are what are referred to as equalities. And equalities are basically two things that are on different scales, but represent the same amount of something, right? So if you had 100 pennies, that is the same amount of money as $1. So they are different sort of units, but they represent the same amount of money. So 10 to the 3 liters is the same amount of volume as 1 kiloliter would be. Questions on that there? Here is again a comparison of sort of the English system to the metric system. If you look at a basic ruler, up on top are inches, on the bottom are centimeters, and we can see that 1 inch is exactly 2.54 centimeters. That is definitely a conversion they expect you to know. That is an exact conversion. That relationship there. Now, when we look at a ruler, since we will be doing measurements and stuff like that, top is inches, bottom is centimeters. What are the little guys? Little guys represent on the bottom? They are millimeters, actually, yeah. So they are millimeters, all right. 10 millimeters in a centimeter, yeah? So each of the small guys down at the bottom here, each of these little guys, those guys are millimeters. So if you count 10 of them, you get 1 centimeter in that particular case, yeah. So it's good to know how to do this. Let's talk about volume. Volume is the three-dimensional sort of space occupied by a substance. Volume's SI unit is meters cubed. Now you may be saying, well, a meter cubed, meter sounds like a length measurement. And when you cube like a length measurement, it becomes a volume. So for example, If you were to measure like a square solid, and you took the length times the width times the height, and you did each of those measurements in centimeters, you would have centimeters times centimeters times centimeters. Each of these individual measurements are length measurements. But when you multiply them all together, you get what is known as a cubic centimeter. And a cubic centimeter is actually a volume. So if you take, for the most part, any length measurement in cubit, by doing some type of measurement like that, you are actually looking at a volume rather than length or distance or something like that. Some very common volume conversions that we see: 1 decimeter cubed is equal to a liter. These guys right here definitely need to know. 1 cubic centimeter is equal to 1 milliliter. That is a 1-to-1 relationship. So 1 milliliter is equal to a cubic centimeter. And probably the conversion you will use the most with volume is this one. In 1 liter, there is 1,000 milliliters. Now, that is definitely one that you should know. And when you look at, say, that prefix table that we saw earlier, where we had milli was 10 to the minus 3, that is the same conversion as there is 10 to the minus 3 liters in 1 milliliter. Now, how do you get that? Well, you could just divide to the other side the 1,000. This guy then becomes 1 milliliter, and this becomes 1 times 10 to the minus 3, or 10 to the 3 liters. So that is also the same conversion. So sometimes people will use the prefix version. Most people will use sort of this version of it. That is probably, again, the most common sort of conversion that we use in volume. And it's for a couple of reasons. One reason that you'll quickly see when you do the labs, most of the time when we take volume measurements, they're in units of milliliters. So it's a very common unit that when you're, say, in the laboratory or something like that, and you take a volume reading, milliliters is definitely one that is used a lot. But in a lot of formulas, you need liters. So a lot of times you're converting those milliliters to liters. And a lot of times you're sort of converting it back the other way, liters to milliliters as well. So that definitely is one. So 1 milliliter equals a cubic centimeter. They're both volumes. It is a 1-to-1 conversion, and one that you see a lot. Now, mass is the quantity of matter that is present in an object. Matter is basically anything that occupies space and has mass, so pretty much anything. And we typically will get the mass of an object by using what we see here. This is an electronic balance, and that is, I guess, a fancy way of saying this scale. So we use an electronic balance to weigh things and get the mass of an object. The SI unit for mass, as I mentioned before, is a kilogram. And again, in terms of knowing, you should probably know these relationships here. 1,000 grams is 1 kilogram. That is definitely a very common conversion that we see a lot in here. Milligrams as well. If you want the bigger number conversion, there's 1,000 milligrams in 1 gram. That is also one that we use a lot as well. So those are two very, very common sort of units of mass that we come across for sure in chemistry. Now, there is a difference between mass and weight, and it's important to sort of recognize that difference. When we talk about weight, it does refer to the force of gravity exerted on an object, but the mass is sort of independent of the force of gravity. So your mass here and your mass on the moon will be the same. Your weight here and your weight on the moon will be different because the force of gravity is different there versus here. So in chemistry, though, when we do use a balance, we do call that the process of weighing something, but you should not refer to it as a weight. You should actually refer to it as a mass. And the reason you should refer to it as a mass is because the modern day balances basically take out the force of gravity associated with it in their sort of programming. So what you're weighing is a mass. So when you do weigh something, you should refer to it as a mass rather than a weight. Any questions on that there? So let's talk a little bit about temperature conversions and the three sort of common scales that we come across. The three sort of common scales that we come across in chemistry or in science in general, or in life, I guess, is degrees Fahrenheit, degrees Celsius, and then, as I said earlier, sort of Kelvin. So one of the first things that's a difference between sort of Kelvin, which is a common unit that we use, and Celsius and Fahrenheit is we actually do not use the degree symbol. So if you look up there, that little circle, which is degrees Fahrenheit, degrees Celsius, we do not use a degree symbol with it. It is just Kelvin. So if we had a temperature that was 273 Kelvin, that's exactly how we would say it, 273 Kelvin. We would not say 273 degrees Kelvin. So we don't use that degree symbol. There's also a difference in terms of where water boils on each of these scales. And as we will see, that is also the difference in terms of how we do the conversions between temperature scales. On the Fahrenheit scale, water boils at 212 and freezes at 32 degrees Fahrenheit. That is the scale we're commonly used here in the US, right, for temperature, right? They take your temperature, the temperature outside, that's very common that we use. The metric system typically uses degrees Celsius, and on degrees Celsius, water boils at 100 and degrees Celsius and freezes at 0. That is definitely something that you should know just going through your chemistry career. 0 and 100, kind of the normal freezing point and boiling point of water is really, really important. A third temperature scale, as I mentioned, is the absolute temperature scale, later renamed for Kelvin as the Kelvin temperature scale. And water boils at 373 Kelvin and freezes at 273 Kelvin. And these three scales, I'll be honest with you, probably outside of chapter 2, you're probably not going to see too much Fahrenheit pop in and play in terms of temperature readings in chemistry. Definitely Celsius will always be there. And that's really because most of the time when we do take temperature readings, our thermometers give it to us in Celsius. So it's a very common sort of unit in the lab, for example. When you get there and you look at your thermometer, it's going to be Celsius on the scale. It's not going to be Fahrenheit. And that's a very common unit. Much like sort of milliliters and liters and so forth, pretty much everybody needs to be converted into Kelvin when you do a sort of chemistry formula in terms of temperatures. So that conversion is used a lot. So outside chapter 2, Kelvin and Celsius is definitely the two that you're going to see the most. And I would say probably most of the time you will be converting between Celsius to Kelvin is probably most of the time what you're going to be doing, and occasionally Kelvin back to Celsius. So again, here's our differences between boiling and freezing points of water. And if we look at the scale there for Fahrenheit, we can see there's about 180 degree difference between freezing and boiling. On the other two scales, there's about 100 degree difference or 100 unit difference between boiling and freezing. And that's the same thing that we see on the other side there in terms of freezing. That is what gives us, as I mentioned, sort of our conversion between the three different temperature scales. And you do need to know all these. And in fact, I'm going to fix this one because here they're super specific. So Let's talk about the conversion between Kelvin and Celsius or back and forth. If you want the temperature in Kelvin, you will take the temperature in Celsius and you will add 273.15. They actually do want you to use the 0.15 here. I would say most people will just use 273, but here you should get in the habit of using 273.15 because they, for some reason, would like you to keep that. Our lab manual will use 273.2, but 0.15 is typically, they do want you to keep that. By the way, if we had to go the other way and we want the temperature in Celsius, it would be the temperature in Kelvin minus 273.15. You definitely need to know. And this, again, I would say is probably the one that you're going to use the most here in chemistry. I say this is probably the most you're going to use, again, converting Celsius to Kelvin. That sort of 180-degree difference between boiling and freezing is our conversion between Celsius and Fahrenheit. So if you want the temperature in Fahrenheit, I'll write it up here since it's getting cut off there on the bottom. 1.8 times the temperature in Celsius plus a 32. Also need to know that. And if you want the temperature in Celsius, it is the temperature in Fahrenheit minus 32 divided by 1.8. Now, if you have a value that is in, say, Fahrenheit, and you need it in Kelvin, you do have to kind of go Fahrenheit to Celsius, Celsius to Kelvin, and vice versa. If you have Kelvin and you kind of go all the way back the other way, you kind of have to go through those processes. So you do need to know all 3 or 4 of those conversions. Like I said, outside of chapter 2, you're probably going to mainly focus on the top one there, but you do need to know the other ones as well. Now, when we do temperature conversions, because there are differences in how people may do the calculation. So, for example, here on the bottom there with the 1.8, that is the same as 9 divided by 5. You might have learned when you were younger as well to convert between those two scales. Some people use 1.8, 1.80, 9 over 5, and so forth. So there's a lot of variation in terms of temperatures and sort of what you should end up with your answer in terms of significant figures. And we're going to talk officially about significant figures coming up, but we're going to talk a little bit about it here in terms of temperature because we do not follow typically the hardcore rules of significant figures when we're doing just a simple temperature conversion. So if you're only converting temperature from one scale to the next, we typically do not follow like the strict significant figure rules because there is a lot of those variations. Again, some people could be using fractions, some people using 1.8, 1.80. So there's a lot of variation. So the general rule is when you do a temperature calculation, your answer should look like the original temperature number. And that means if your original temperature number was a whole number, when you do the conversion, you should convert it to a whole number. If your original temperature went to 2 decimal places, you should convert it to 2 decimal places. So, and that is a sort of specific rule just for temperature conversions. You want to make your answer look like the original number when you're doing that. So, just for temperature conversions, your answer should look like original number. And again, however far the original number went to, that is where you should take your conversion to. Any questions on that there? All right. Then let's try some. Grab your calculator if you got one. Hopefully you do. And do each of these conversions. Temperature on a balmy day, 28.5 degrees Celsius converted to Kelvin. We got 41 degrees Celsius. What is it in Fahrenheit? And we got 160 degrees Fahrenheit. What is it in Celsius? Take a few moments there. Make sure you can punch that all in correctly. All right, let's take a look, see how you're doing. So first one, we are going from Celsius to Kelvin. So again, our temperature in Kelvin is going to be our temperature in Celsius plus, again, 273.15, as they want you to use that number. So we're going to go 28.5 plus a 273.15. And again, I pop that into my handy dandy calculator somewhere. And that's going to give me a 301.65 Kelvin. Again, in terms of what I was talking about earlier, in terms of our sort of answer, our original number here did go to 1 decimal place, and that is where we would want to convert it to. So we do have to look at the 5 and above. We do round up, and we would want to give our answer as 301.7 Kelvin. And again, a reminder that that is sort of a specific sort of rule we'd follow just for temperature conversion. Any questions on that? Also, as you can see, no degree symbol on the Kelvin, on the K, so just a capital K. Taking a look at the next one, we have Celsius, and we're looking for Fahrenheit. So our temperature in Fahrenheit is going to be 1.8 times our temperature in Celsius plus a 32. So we're going to go 1.8 times 41 plus a 32. We're going to go 1.8 times 41 plus 32 here. That's going to give us on our calculator 105.8 degrees Fahrenheit. Once again, we're going to look at our original number here, and we do see it is a whole number in this case. So we will want to round this to a whole number. Once again, we do want to look at the 8. That is above 5, so we're going to round up. So a 106 here would be our proper number. Any questions on that there? Lastly, we got some pork at 160 degrees Fahrenheit, and we're looking for Celsius. So our temperature in Celsius, temperature in Fahrenheit, minus 32 divided by 1.8. And we'll go over here. So we'll go 160 minus 32 divided by 1.8. And that's going to get us 160 minus 32 divided by 1.8. Looks like a 71.111, a bunch of them, degrees Celsius. Once again, looking at our original number in this case, it is a whole number. So we will go here. That is a 1, which means we just drop the rest of them, and we would end up with 71 degrees Celsius. Any questions on those temperature conversions? So yeah. Yeah, we're going to talk about actual sort of the rules for significant figures, if that's what you're asking. There are certain rules you follow when you do calculations with significant figures. But for temperature, because there's a lot of variation in terms of what formulas people will use, people just follow this sort of general rule for significant figures and your answer. And basically just the general rule is what we did here, which is however far our original number went to is how far our answer should go to. So the first one went to 1 decimal place. Our answer would want to go to 1. The other 2 went to whole numbers, so we would want to take them to whole numbers. Yeah. Other questions? And like I said, when we get to significant figures and the rules, there are specific rules to follow when you're doing real sort of calculations outside of temperature calculations. You want to follow those other rules. Other questions? All right, so obviously here going through these, right, understand the type of measurement. A Kelvin is what type of measure? That is a, yeah, that is a temperature. Yep. Liter is a volume. Meters is a length, right? And kilograms is a mass. So again, understanding what each of those units represent in the type of measurement is really important as well. All right. Let's talk a little about some differences in sort of observations that we take. There is qualitative and quantitative sort of observations. A qualitative observation consists of just general observations about the system. You're really not taking measurements. So, you know, for example, this could be like, hey, it turned purple, right? There was some bubbles or something that happened, a gas was generated. It is things that you observe what's happening, but really no type of measurement. In fact, if you take Chem 1B, if you get to Chem 1B and you do take Chem 1B, you do a bunch of labs that are what are referred to as qualitative analysis. And in those labs, it is nothing more than you do not measure anything. You just go like, 20 drops seems good. That's about a milliliter, right? I'm not going to measure out a milliliter exactly. And you're looking for like colors that develop, solids and colors and stuff like that. There's really no numbers, no measurements that you're making in those type of experiments. And that's all qualitative, which is a really important thing that you should take observations of when you're performing experiments. Something changes color or some type of bubbles or something that develops. Those are important things. Quantitative is all about numbers. It's all about measurement. So when you take a measurement of something, you put something on a balance and it's 56.325 grams, that is a quantitative measurement. You measure out exactly 5.00 milliliters, that is quantitative, right? You want exactly that sort of amount. And that's all about what measurements are. And those are also really important to take. And when you take those type of measurements, you should record, as we've been talking about, not just the number, but the units associated with it so you understand what it means. Really, really important. With a measurement, as we will talk about shortly here, there is always some degree of uncertainty with a measurement. You can't do it perfectly. There's always some type of error associated with a measurement. Now, let's talk about scientific notation. And in chemistry, we oftentimes come across really large numbers or really small numbers. And to handle these really large numbers or small numbers, I'll write it over here. This is scientific notation that we use. And scientific notation has a general formula of n times 10 to the n. And this is a number between 1 and 10, not usually 10. So usually less than 10, but it can be 1, but not usually 10 on the nose. And this little n up on top here is either a positive or a negative value, really depending on how many decimal places you got to move to get to a number between 1 and 10. Why do we use scientific notation? Well, obviously, as you can see there in the example, that is a lot of zeros that you would have to write and try to use in a calculation. There's probably a fairly good shot you're going to lose some zeros along the way if you're like doing a big calculation with that. Or even that really, really small number there, 0.000. I lost track of zeros already, right? All these zeros here. You're probably going to lose some zeros along the way. By the way, when you do write a decimal like that, it is actually a really good thing to put a 0 in front of the decimal, like you see here, and not just go decimal zeros. It should be like 0 point something. It's a really good habit to get into so numbers don't run together as you're writing them and stuff like that. So we do use scientific notation to help us take care of these big numbers or small numbers. So if I had 125 and I wanted to write this in scientific notation, in this particular case, although there is not a decimal point actually written in the number, we do actually, for scientific notation purposes, assume it's at the end. And if I go to the left, that would put a decimal point there. That would actually get me to 12.5, which is obviously greater than 1 and 10, right? So that's not enough. I got to go one more decimal place. That's going to give me 1.25, which is a number between 1 and 10. And this would be 1.25 times 10 to the 2. It is a positive exponent because I moved the decimal place to the left to get to a number between 1 and 10. Or if you want to remember it, numbers greater than 1 or larger numbers have positive exponents, right? So 125 is, above 1, so it has a positive exponent. If I had 0.03256 and I wanted to turn this into scientific notation, I would actually have to move the decimal place to the right. If I move it to the right there, that is 0.3, which is less than 1. So I need to keep going to 3.256 times 10 to the minus 2. The 2 in this case, again, is how many places I moved the decimal place. And I moved it to the right, so it's going to be negative in this case. Again, smaller numbers typically will have negative exponents. Yeah, and that'll get you there. So that is really important when you write something in scientific notation to write it correctly. You should never write like 20 times 10 to the something or 100 times 10 to the something. Again, it needs to be 1 is okay. 10 is not okay, so it's got to be less than 10. It could be 1 and above, but it has to be in numbers somewhere in between there. We will talk later on in a second a bit about significant figures, but when we do write a number in scientific notation, all of the numbers, all of these numbers before the times 10 part are significant figures. And again, we'll talk exactly what significant figures are in a second. But if you do see a number written in scientific notation, there is a reason why there is so many numbers before the times 10 part, because they are significant. So for example, this guy would have 3 significant figures, as all of those are significant. This guy would have 4 significant figures, as all those guys would be significant as well. You never want to lose any significant figures when you go from like scientific notation to decimal or decimal to scientific notation. There can be times, as you will see in problems, that the only way to give the right answer for a problem in terms of significant figures is to write it in scientific notation. That's the only way you could actually give the answer that has the right number of significant figures. There can be no way sometimes in decimal form to give the right number of significant figures, and sometimes that's the only way. And it does give you a lot of flexibility in terms of significant figures because, for example, let's just say I didn't need 4 significant figures, but I just needed 3. I could just rewrite this as 3.26 times 10 to the minus 2. Now I have 3 significant figures. Let's just say, hey, I just needed 2 significant figures. I could rewrite it 3.3 times 10 to the minus 2. Now I have 2 significant figures. So you could actually almost lock in as many significant figures as you want when you write a number of scientific notation. And it's important to not lose any along the way when you do that. And it's also just as important not to add more along the way, that you shouldn't have when you do that. Any questions on writing that there? Yeah. Yeah, you don't have to ask. Go ahead. Yep. Now, probably more important than writing numbers in scientific notation and being able to write them from scientific notation into decimal form or decimal form into scientific notation is being able to do it on your calculator. And most people do not know how to properly punch numbers in on their calculator in scientific notation. So we're going to talk about how to do it in general for all calculators. This is, again, the approved calculator for quizzes and exams. We'll talk about sort of how it does it on this one so you have an idea as well. But when you look at your calculator, there is a exponent button on your calculator. On most calculators, that exponent button is one of 3 buttons usually. It is either an EE button, it is either an EXP button, or on some of the newer ones, which are kind of like two-tone. I guess they're not new this often anymore, but they're relatively newer on the market. They actually have a times 10 to the n number. Those usually are two-tone in color. Like the outside color of the calculator is a different color than like the inside. And it usually has like a little wheel sort of on those type of calculators. So if you have this one, or you have calculators that has either of these buttons, there are a couple different ways that you punch a number into scientific notation. So let's just take a number like 1.25 times 10 to the minus 3, and we wanted to actually punch that in our calculator correctly. The other 2 buttons that are important is your negative button or change of sign. It usually looks like this, or it looks like this. It is not the subtract button, by the way, which is a common error sometimes people will make. They'll use a subtract button for like the negative button, and the calculator will go error and stuff like that. So if you're going to punch this in to a calculator that has either of these 2 buttons, which this approved calculator does, and a lot of buttons do, our calculators do, you would type 1.25. You then would hit your exponent button. And what you would typically see on the screen is 1.25, and a lot of calculators will put an E, or like it will do on this sort of approved calculator, it will just pop up a couple of zeros up towards the top when you hit that button. Now, when you hit that EE button, the exponent button, that is basically, when you hit this button, that is this part of the number. So that represents the times 10 part of the number, which means you should absolutely, positively not hit the multiplication button, should not hit the inverse log button or shift log or anything like that, because you will get the wrong answer, especially later on when you start using the log button with that combination. You're going to be way off on your answer. So all this left is the -3 part in terms of what we need to put in there. So we do just want to hit our negative button, whichever one yours looks like, and then 3, and this will become -3. This will become a negative, and we'll turn this into a 3. And that is the proper way to punch a number in scientific notation into your calculator. Now, if you have this sort of two-tone calculator with this combination, a little wheel and a times 10 part, you just got to put everything in parentheses. Any number that's in scientific notation, you got to put parentheses, because frankly, your calculator was programmed really crappily and it doesn't know how to do it, and it mixes all the numbers together. So you need to open a parentheses. You need to punch in 1.25 and then hit your times 10 to the n button. And on your calculator, you'll have 1.25. We'll put the times 10. You'll have a little blinking box up on top that's blinking at you. That is where we will continue to put the rest of it in the same way. You'll hit your negative button and 3. This will then become 1.25 times 10 to the -3. And your little box is now to the right of the -3, blinking up on top. This is where the wheel comes into play. You hit the right-hand side of the wheel, and it will bring this little blinking box down to a regular size, basically. So you do that, and it will become 1.25 times 10 to the -3 with a regular box blinking. And now you can close your parentheses, and you will now have something on the screen that looks like this. And that would be what you need to do. Obviously, there's a lot of steps. I did each step individually, but you get the hang of it if you need to do it that way. But that is definitely for the most commonly calculators out there, how you want to properly put that into your calculator. You definitely want to use your exponent button. You do not want to use what a lot of people use is they look at their calculator and they find the little log button and it's like 10 to the x. That looks like the right thing. That is not the right thing, by the way. Do not use that button. What you will find yourself going is, I don't understand. Like the front part of the number is good, but the exponent part is not so good. You'll always be off on that top part. And again, it will be magnified later on, especially in our class when we do acid and bases, and we actually use the log button in the calculation. It's just going to magnify sort of the error along the way. So 100% always want to make sure that you use your exponent button when you're punching things into your calculator. Question on that. So why don't we try one here just to see everybody knows how to punch it in correctly. Let's just do a calculation with them. So let's say we did take 1.25 times 10 to the -4. Let's divide it by 3.2 times 10 to the, we'll do 8. And why don't you also do 3.5 times 10 to the -6 times 4.65 times 10 to the 14. And make sure you see what you get there. I suppose do 24. Let's go big number. All right, so take a moment, punch it in correctly on your calculator. Make sure you're using your exponent button. And we'll see if we get the same answers. I'll do it as well since I made it up. So again, I'm going to write out sort of what you should punch in. You got to go 1.25. You need to hit your exponent button. You need to then hit your negative button and 4, then your divide button, your 3.2 exponent button. This is a positive exponent, so no negative button needed, and 8, and hit equals. If you again have the other calculator, you got to open up that parentheses, 1.25. You need to hit your times 10 to the n, your negative and 4. You got to do your will and close your parentheses, divided, open a new parentheses, 3.2, exponent button, and 8. Again, hit your will to bring it down and close it and hit equal. Out of any of those ways, you should hopefully end up with something on your screen. So for this first one here on my screen, I've got myself, looks like a 3.90625 E, negative 13, or a very common way on a screen. You may see 3.90625 minus 13 kind of popped up on top with like a space and nothing much underneath there, or I may say times 10. So when we give our answer here, we do want to give it as 3.9 times 10 to the minus 13. We will talk about significant figures later. That's not truly important. But the important part and the thing that a lot of people miss when they use their calculator and do this is they ignore the back part here. Yeah. So you want to make sure that you do put the exponent part in there and you're not just writing like 3.9 down as your answer, because that is not the proper answer. You want to make sure that you do include that times 10 part, which is usually to the far right. And again, very commonly people kind of just hit the front number, forget about sort of the exponent part of it. Any questions on that there? All right, looking at the second one there, we'll come down here. We're going to go 3.5. We're going to do your exponent button. Once again, you're going to do your negative button and 6. You're going to hit the times button, 4.65, exponent button. And again, this is a positive, so positive 24, no negative there. That's going to get us here on our screen, 1.6275 E19, or 1.6275, again, kind of a 19 up on top, or a times 10 to 19 up on top. Once again, if we're going to give our answer here, we would go like a 1.6 times 10 to the minus 19. Once again, making sure that we do not forget the exponent part here in the calculator, and we want to make sure that we do put it in there as well. Any questions on how to punch it into your calculator? In my opinion, more important sometimes than being able to write it or and identify it. Any questions? If you're not sure, just at some point come up with the calculator and we'll figure it out together. But again, the one that you are going to use for quizzes and exams does have an EE button version of it, and it will also give the display more like what we see over here with kind of the space and the exponent towards the top. Any questions on that there? Cop. All right, so let's take a look at some of these, again, scientific notation examples. None of these numbers are negative. That's just from PowerPoint. But here we do need to go 1 and 2 places to the left. And we will end up with 5.68762 times 10 to the positive 2. Again, a large number will give us a positive exponent. This is a case, as we will talk about when we get to significant figures, all those numbers in the first number are significant, and that is why we hang on to all of the numbers when we put it in scientific notation. Here, we got to go 1, 2, 3, 4, 5, and 6 places to the right. That is what's going to give us times 10 to the minus 6 here. 7.72 times 10 to the minus 6. Here, only the 7, 7, and the 2 are significant, so that is why we got rid of all those zeros in front. They are not significant. And again, we'll talk about that later on. Not written here, but assumed to be here are decimal 1, 2, 3, 4 places. gives us times 10 to the 4 here. 1.25 times 10 to the 4. The two zeros, as we'll talk about, are actually not significant, so that is why we dropped them off the end of the number. And our last example there, 0.135, just need to go one place to the right. Going to give us 1.35 times 10 to the minus 1. If you do have a number that is written in scientific notation, and you need to put it into decimal form, again, you just kind of go opposite. So when you look at that, the 2 means is how many places we're moving in decimal. Remember, negative is a small number, which means to make this number smaller, we have to go to the left in this case, right? Because that's going to put a 0.1 versus if you go to the right, that's 13. So bigger to the right, smaller to the left. And we would go 1 and 2 places and put some zeros in there. And that would give us 1 and 2. So 0.0135 would be converting that into decimal form from scientific notation. Obviously, if you had a bigger positive exponent, we need to make this number bigger. So we got to go that way and add some zeros. And we would end up with something like that there. Any questions? I'll go in either way. Scientific notation, how to punch it into your calculator. All right. Let us talk then about measurements and taking measurements and the uncertainty in a measurement. So when you take a measurement, there is always some degree of uncertainty. There is some degree of guessing involved when you take a measurement. The degree of guessing is related to the piece of equipment you're using. Some are much better than others to take measurements with. Some, there's a little less guessing than others. But there is always something that is estimated when you take a measurement. So let's just take a very simple example of a ruler. Actually, let me erase my ruler and try that again. Draw a better one, maybe. Let's try that this way. We'll call that 1. We'll call that 2. We'll do a little centimeter action. I'll put a classic arrow up there. All right, so we want to take a measurement here using this ruler of the arrow. So whenever you take a measurement, there's really 2 sort of markings you want to look at on that piece of equipment. And you always want to look at it because even if it may be the exact same piece of equipment that somebody else is using next to you, it may be made by somebody else and they put a different scale on it. So you always want to look at the scale on the equipment that you're using. There are typically what I refer to as large markings and small markings. Now, large markings will typically have an actual number. So large markings typically will have numbers next to it. I take a peek here. I got me a 1 and a 2. So the difference here in our large markings between 1 and 2 is how many centimeters? Difference between 2 and 1 is? That is not the hard question. 2 minus 1 is? There we go, 1 centimeter. Not everybody at once, it scares me. All right, so big markings is 1 centimeter. Now there's a bunch of little markings that are between those two. So between the big markings, there's a bunch of little ones. And you want to make sure that you do count correctly how many there are. So when you're counting the smaller markings, you always want to start at the one that is past the last large marking. So for us, the last large marking is the 1. So we want to go start counting here. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we do want to stop counting at the next large marking. So when you're counting the small guys past the first marking, the first large marking, and stop at the next large marking. That is 10 smaller markings between each of those larger markings. So if I take my large marking and divide it by 10, that tells me that each of the small markings in this case represents 0.1 of a centimeter. So if you take 10 or 1 divided by 10, you get 0.1. That means if you come to this marking here, this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2. First off, any questions? All right. When we do take a measurement, there should always be numbers that no matter who looks at it, pretty much everybody should agree. So if you were to look at my arrow here, everybody should agree it is more than 1.4, but it's not quite 1.5. So it's somewhere in that ballpark of 1.4 and 1.5. It is at least 1.4. So you want to record 1.4. This is what is sometimes referred to as recording all the certain numbers. So whenever you take a measurement, you want to record all of the certain numbers. And again, those should be numbers that everybody should agree upon. Now, as I mentioned a second ago, obviously my arrow doesn't stop exactly at 1.4. It doesn't hit 1.5. It is somewhere in between the two. And that is where the uncertainty is. That is where the estimate is going to come into play. If I just kind of draw a line down, I may look at that line and go, well, I think it's kind of halfway between the two markings. And halfway between the two markings would be a 5. And obviously we would record our units, which is centimeters. This is what is referred to as the first uncertain number. And it's uncertain because somebody else may look at it and go, I think it's like a little bit past half. So maybe it's like a 6 or something like that, right? Or maybe somebody may look at it and go, well, maybe it's just a little shy of the half mark. Maybe it's more like a 4 or a 3 if it's really shy, right? Or if it's just above like the 1.4, maybe you record a 2. So the first thing is it doesn't always have to be like a 5 at the end. It should represent kind of where the line ends. For example, if it's closer to like the 1.4, maybe you would record like a 1 or a 2 at the end. If it's closer to the 1.5, maybe you record like an 8 or a 9 maybe at the end. But we would record these together. Now, the reason when we take a measurement that you want to record all the certain numbers plus the first uncertain number is when you do that, and you record all these guys together, that is pretty much what significant figures are. Which would mean this particular measurement would have how many significant figures? This would have 3 significant figures. All the certain numbers plus the first uncertain number. So every one of these numbers here would be a significant figure. Now, it does depend, obviously, on the piece of equipment you're using as to how far you take the reading to or what it represents. So let's just say we had something like this, like a horribly drawn graduated cylinder-ish, sort of. And about 20. We'll put a liquid in there, something like that. And we want to take a measurement. And by the way, when we do take a measurement of a liquid in a glass container, you typically will see dramatically drawn here curvature of that liquid, maybe not so much of a big U like that, but you'll see some type of curvature of that liquid. This is what is known as the meniscus. And typically speaking, when we have a U-shaped meniscus, we want to take a reading from the bottom of the meniscus. And what is actually happening in this case is the attractive forces between the liquid and the glass are stronger than the attractive forces between the liquid and itself. And through capillary action, where the liquid touches the container, it starts to climb up the walls. So it gives it that U type of shape that happens. That is why we take the reading from the bottom of the meniscus, because in the middle here, that's not touching the walls. It's not going up the walls, right? It's not climbing. It's actually where the volume actually is. And that's why we want to take the reading at that point. Probably 99.9, maybe 100% for you guys. Meniscuses that you will see, and sometimes they're easier to see or harder to see depending on the glass orders you're using, will be this U meniscus. It is possible that the meniscus can actually go in the other direction and actually curve upwards and make more like an N type of looking type thing. Mercury is very commonly will do that. And that's because mercury actually is more attracted to itself than the glass. So it actually goes down on itself and makes this sort of upwards down. And that's why if you had a situation like that, you would actually read from the top of the meniscus, because again, that's not touching the glass and that's really where the liquid is. But I would say almost 100% of the time, if you guys are looking at a meniscus, it's probably going to be the U-shaped meniscus, especially in school because they took out mercury pretty much barometers and stuff like that. So you don't really have mercury too much around that you would look at it. So we would want to still do the kind of the same thing which you did on the last one is we want to figure out what our large markings are here. So we got 10 and 20. So our large markings, the difference between that is 10 milliliters, right? So if you take 20 minus 10, that's 10. We again want to count up how many little markings we got going on between, starting after that last large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, ending on the next marking there, large marking. So if we take 10 divided by 10, that means that each of our small markings in this case represents 1 milliliter, right? So if we take 10 divided, you get 1 milliliter. That means that this marking right here should be 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, all the way up to the top. And if I draw my line where my meniscus is, very bad straight line-ish, we'll kind of estimate it there. We can now take the proper reading. When we look at a not so straight red line there, we could see it is at least 14, so we would want to record 14 in this case. And again, we could look at the here, and maybe in this case, when you look at it, kind of looks like maybe it is a little bit closer to the 15 than it is to the center. So maybe you record 14 point, we'll call it maybe 7. And again, we do our milliliters. Again, these would be our certain numbers. This would be our first uncertain number. And that means, again, in this case, this measurement would have how many significant figures? This should have 3 significant figures, right? So this would have 3 significant figures. The estimated digit in this case is the 7, that's right? So what we're really saying when we take this measurement is, I think it's 14.7, but hey, maybe it's like really 14.8, or maybe it's like 14.6, somewhere in that little decimal point. I'm not quite sure, but I'm making a pretty good estimate as to where I think it should be. Any questions on that there? Now, as I mentioned before, it's really important to make sure you do look at the scale, because not all scales are the same. So we took this graduated cylinder. Let me do this. Maybe I'll put my liquid here. Why don't you take a moment, my bad liquid here, and why don't you take a reading as to what you think the proper reading should be with the right number of significant figures. So why don't you take a moment and think about what you think it should be. All right, so let's see if you are right or not. So we'll start with our large markings. So I have a 10 and a 20. So once again, just like the other one, the difference in our large markings here is 10 milliliter difference between those two. When I count up my smaller markings that are between those two, I have 1, 2, 3, 4, and 5 in this case. That means that if I take 10 divided by 5, each of my small markings in this case is actually 2 milliliters in this case, right? So that would mean that this marking here would be 12, 14, 16, 18, and 20. Now, if I draw my straightish line around my meniscus there, when I take my reading at this point, I have 14. It's between 14 and 16. What is the number between 14 and 16? That is 15 milliliters in this case. That is the best you could do on this particular scale, because when we look at 14 and when we look at 16, there is not enough room in that space for you to figure out where 14 stops and 15 begins, right? We could do that on the other one because it's just one difference, right, between them. But here you can't really figure that out. So the best we could do is actually only record this as 15 milliliters. By the way, that would have how many significant figures in this case? It would have 2 significant figures in this case. What one would be the estimated digit? It would be the last significant figure, which would be the 5 in this case. And we're basically saying, I think it's 15, but hey, it could kind of be 16 or it could be 14. This is a much worse piece of equipment to use to take a measurement than the previous one, right? Because we go further out in our measurements, right, in terms of where the error is. Here, the error is in like the first decimal or the first place, the ones place, rather than say like the tens place or the hundreds place on the previous ones. Any questions on that there? So it's really important to sort of figure out, you know, how far you can take the reading. And those are really the first 2 things you want to kind of do is figure out what's the large markings represent, what does the small markings represent, and how far you can take that reading. Now, you could absolutely, if you are confident in what the smallest markings represent. So if you look at this scale and you're like, I am pretty darn sure that the smallest markings on this thing definitely represents 0.1 centimeters. All you have to do is take the 0.1, the smallest marking, and divide it by 2. So if you take the 0.1 centimeters and divide it by 2, you will end up with 0.05 centimeters. And sometimes people will include a plus or minus. That is sometimes referred to as the tolerance of the equipment. And here at Saddleback, they do like you to include that when you take measurements. So if you were to include that, you would write 1.45 centimeters plus or minus 0.05 centimeters would be the proper way to take a measurement here in your journeys of Saddleback chemistry. Yes. By the way, what does it actually tell me? When I get 0.05, how many decimal places is it? 2 decimal places? How many decimal places did I take my answer to? 2 decimal places. It will tell you how far you should take the reading to. So if you can for sure identify what the smallest marking represents, if you divide it by 2, you want to take your actual reading to however many decimal places that may be. So if we come here to this one, the smallest marking is 1 milliliter. I divided by 2 gives me 0.5 milliliters. That is 1 decimal place. That is exactly where I took my reading to, 1 decimal place. And if I were to record this like you should as a measurement, 14.7 milliliters plus or minus 0.5 milliliters. Again, would be the proper way to record that here, especially in laboratory. They expect you to kind of do that when you do take measurements. So anything that's a measurement, you do expect you to kind of include that tolerance of the equipment. You do not need to include it in calculating, but in actual measurements that you take, if you want you to include it. By the way, it even works for this weird one here. If you're confident that is 2 milliliters, take my 2 milliliters divided by 2, that's 1 milliliter. That's a whole number. That's exactly where I took that one to. And I would record 15 milliliters plus or minus 1 milliliter in this particular case. Any questions on there? Now, another very common error, if you will, that people make is, we'll just kind of go back to our original ruler. And let's just say my arrow was like dead on that line right there. This is obviously the same rulers we used on the very first example. So just like on the first example here, we have large markings that represent 1 milliliter. We have smaller markings, there's 10 of them, represents 0.1 centimeter, not milliliter up on top, centimeter up on top. And again, that would mean that if we look at the smaller markings here, that is 1.1, 1.2, 1.3, 1.4, 1.5, and so forth. So if my line is right on the 1.4 line, I'm going to record 1.4 centimeters, 1.40 centimeters, 1.400000 centimeters. Is there a difference in terms of how I record it, or does it matter if it's right on the line? What do you think? Well, I'm assuming if I'm asking a question, there might be a difference. So let's see what the difference might be. Take the very first example here, right? If you were to record with this equipment here, 1.4 centimeters. What you're really saying is, I think it's 1.4 centimeters, right? But this guy has how many significant figures written as 1.4? This has 2 significant figures. The uncertain digit would be the 4 in this case, right? So when you take that measurement at 1.4 and record it that way, you're saying, I think it's 1.4, could be 1.5, could be like 1.3, with like a plus or minus 1 of that uncertain. So you're basically saying, based on this piece of equipment that you got, is I think my little line is, somewhere in that area. That is a lot of error, right? That you have, because as you can see, your line is kind of nowhere near those, right? It's in the middle of all that. And that is inserting a lot of error. Now, you would probably not want to do that. Let's take a look at this one. How many significant figures should this one have? So when we record a measurement, right, we record all the certain numbers, the first uncertain number, they're all significant. So if I recorded this as my measurement, that means how many significant figures does it have? 3, yeah. So this would have 3 significant figures. Uncertain digit would be, in this case, it would be the 0th. So when you do this measurement, you're saying, I think it's 1.40, but maybe it's like 1.41, maybe it's like 1.39. You are now saying, I think we're somewhere in like this area. A lot less error in that measurement, right? And a lot better of a measurement. And you're able to do that based on the scaling that you have on this equipment. Because as we know, if we take this guy and divide it by 2, 0.05 centimeters plus or minus, that is 2 decimal places. That is actually how you should record this. Because if you did what we did here on the left and you lopped off a significant figure, right? I just made that measurement pretty crappy, right? There's a big room of error in there, right? That should not be there based on that equipment. So you do not want to lop off numbers that should be there. If you feel like it's exactly a number on a line, you do need to add a 0 to maintain the right number of significant figures. Otherwise, you're making your measurement a lot worse than it should be. That's a very, very common thing when people take measurements. Everybody's perfect. Oh, it's exactly like 1.4. Or they go to the balance. Oh, it's exactly 52. I didn't measure anything else. So you want to make sure that you record numbers correctly. By the way, if you have a digital display, you should always record all the numbers. They're all significant. That's why they are displayed. Yeah. So if you have anything that's digital, like a balance, a scale in the lab room, you want to make sure you put all the numbers that are there. That's also a very common error people make. They go up and, like I said, just go, oh, it's like 52.365. 52 seems good. I'm perfect all the time. By the way, obviously over here would be a not good one, right? Because the one on the right would have how many significant figures if that was an actual measurement? I don't know, I lost track here, but it should be all of them. So 1, 2, 3, 4, 5, 6, 7. It would have 7 significant figures. That would mean the uncertainty in this measurement would be which zero? The one at the very end. And there is no way on this scale that you could take that measurement, right? There's no way you could get it that far to the right. And that makes up a good point as well. You should not add zeros. That should not be there either, because like when you take off zeros, you're making your measurement a lot crappier. When you add zeros, you're making it a lot better than it should be. So you want to always give it to the right number of significant figures. And again, the scale determines that, and you don't want to add more because it makes it better, or drop off some because it makes the measurement worse. Any questions on that? Yeah.
That wants us to write the plus or minus section, one third and like 1.4 seconds, but we approximate to write the plus or minus. How would we write it for the?
Are you talking about this? How we get to 2 decimal places? Mhm. Correct. Yeah, you would write 1.4 plus or minus 0.05 centimeters. And you would come to that based on the same thing that we talked about previously. Before you took your measurement, you would want to look at your ruler, figure out what the large markings represent, what the small markings represent. And from just knowing what the small markings represent, that will tell you that 0.05, and that really you should take it to 2 decimal places. So like I said before, if you're uncertain, and we're definitely doing measurements and a whole experiment on measurements next week. But if you are not sure how far you should take the reading to, but you are very certain of what those small markings represent, again, the easy thing to do is just divide it by 2. And however far it goes is how far you should take that reading to. And it kind of will tell you kind of how far to take the reading to when you divide it by 2, without having to maybe sort of think about it. As long as you can nail down what each of those small markings represent, divided by 2 tells you how far to take the actual reading to, and you'll always be in shape. Yeah. Other questions? So as I mentioned a second ago, it is custom, obviously, to record all the certain numbers plus that first uncertain number when you're taking a measurement. And again, all of those things together are significant figures. And for the most part, most people assume that sort of the uncertainty is plus or minus 1 of that last significant figure. Now, in the examples we sort of looked at, for example, the uncertain number or the estimated number has sort of always been the last number that's written, and it is not always the case. But the uncertain number or the estimated digit should always be the last significant figure that is written. So the last significant figure is where the uncertainty lies, not always the last number that's written. So very commonly that sometimes occurs. And you just want to watch out for that. But most of the time it is that last number, but occasionally it is not the last number is written. That is actually the uncertain or estimated digit. So that brings up a good point of when we do take measurements of accuracy versus precision. And accuracy tells us how close a measurement is to the true value, while precision tells us how close a measurement is to a group of numbers. So the classic example, as we will see shortly here, if we were going to maybe throw some darts, the goal when you throw darts at a dartboard is to hit the center of the bullseye. And if I take my darts and I throw them, and I hit here, I hit over here, hopefully nobody was standing there, missed the board, and I hit over here, am I accurate? The goal here is to hit the center, and here I am not very accurate, right? I'm all over the place, probably injured somebody there standing next to the dartboard. Am I precise? I'm also not very precise, right? Again, I'm all over the place, right? Some are on the left side of the board, some are on the right, some didn't even hit the board. So I gather up my darts and my pride a little bit, and I go, all right, we'll do double or nothing. So I take my darts and I throw my darts again. and I go boom, boom, and boom. I got them all on the board, barely. Am I accurate? I am not. Again, the goal here is to hit the middle, right? Am I precise? I'm precisely not accurate, right? And that can happen a lot. You could do an experiment multiple times wrong the same way every time, right? And get the same answer, but you might be doing it wrong every single time you do it. So it is possibly very precise, but not very accurate, which obviously is not what you're looking for, right? When you do an experiment, you want to be accurate and precise. But again, you can sort of repeat the same error over and over again and not be very accurate. Now, when we talk about accuracy and being accurate, we oftentimes talk about percent error that we'll talk about maybe a little bit in the semester. And when we look at percent error, we're looking at like a low number is what we want, something really low, close to the true value. Well, if we look at precision, oftentimes we look at deviation, standard deviation, percent deviation, and we also want a low number for that. And again, we look at precision in terms of like reproducibility. That's why in a lot of cases we do multiple trials of the same experiment over and over again to see if it is reproducible, right? If we have a lot of precision, and we also want to be pretty accurate. So I go the dartboard. We'll clean our darts up. And now I change out my darts too. Now that they're red ones, they're much better. And I hit dead center, all three of them. Am I accurate? Am I precise? I am precisely accurate in this case. And that again is the goal, right? We want to get the right answer, and we want to be able to reproduce doing the experiment multiple times and get the same answer every time, right? And that's sort of the goal as to when you do experiments. Any questions on that there? And that's what this little dartboard represents. Again, here on the left, we're inaccurate and imprecise. We are precise but not accurate. And again, dead center there, accurate and precise. All right, so take a moment here and see what you could do in terms of the measurement, what it should be. These big numbers should be on the big lines, basically. I think things got a little shifted there. I'll blow it up so maybe you can see it a little bit better. All right, what is the proper reading should be? Maybe with the plus or minus on there. So I think things shifted, so I don't think any of those answers are going to work. So take a reading based on the scale of what we see, and we'll just kind of ignore those answers, I think. That's some shifting there. All right, let's take a look at what it should be here. Again, this is going to be really 2. That's going to be 3. So our big, large markings, right, is going to be 1 centimeter in this case, as that is the difference. If we sort of count where our smaller markings are, we're going to start counting here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we got 10 smaller markings. So that's going to put our smaller markings 1 divided by 10, 0.1 centimeters, right? So on how it shifted here, it looks like this should be 2.5. That would be 2.6, 2.7, 2.8, and 2.9 in this case. So it is at least 2.8. So we would want to record that. Now, again, the estimate here is not exactly 2.8. It's not exactly 2.9. Here, I do believe the arrow is hanging a little closer to the left-hand side there marking than the right, and definitely not the middle. So maybe you record like a 3 and a centimeter. Now, in terms of our plus or minus, right, we could take our smallest marking and divide it by 2. That will give us plus or minus 0.05 centimeters. And that is 2 decimal places, which is where we took our measurement to. And we would have plus or minus 0.05 centimeters. Clearly, none of those bottom answers as things kind of shifted there, I think, in the PowerPoint slide. Any questions though on that one? By the way, how many significant figures would this have? This would have 3 significant figures. The estimated digit in this case would be the 3 at the end, yeah? So any questions on that one there? Yeah. I feel we got the same situation going on here, so let me roll with this one here. See what you come up with. And again, this is 8. I think that probably should be pretty good. Let's see. So again, if we look at this scale, we got an 8 and a 9 as our large markings. So again, our 1 centimeter, we should again have kind of a similar deal. I think 1, 2, 3, 4, 5, 6, 7, and 10. So we do have 10 small markings going to get us our 0.1 centimeter. Once again, we can divide that by 2 right off the bat if we're confident on that. And that will tell us that we do need to take it to 2 decimal places for sure. And if we do that, it is at least, this would be 8.5, 8.6, 8.7, 8.8. So here we are just 8.7 and about halfway there. So we'll do the 5 plus or minus 0.05 centimeters in this case. Any questions on that one there? Again, this would also have 3 significant figures in this particular case. Okay. Now, as I mentioned earlier, when we do look at any type of liquid within a glass, you will see that meniscus, that curvature of the liquid. And again, we are looking at the bottom meniscus in most cases when you have the U meniscus. And if we kind of zoom in here to kind of take a looky, our big markings kind of in that area, 30 and 40, our large markings, 10 milliliters in this case. Small markings, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, if we take that and divide that by 10, each of our small markings in this case is going to be 1 milliliter. And that would mean that this would be our 31, 32, 33, etc. We also can, if you want, right at this point, if you're good with the 1 milliliter, we divide this by 2, tells us plus or minus 0.5 milliliters. We now know that when we take this reading, we need to go to 1 decimal place, which is the proper way to take this reading. So if we follow up here, 33, 34, 35, 36. So we definitely want to record 36. Not exactly 36. Again, if you feel like it's halfway between those two, 36 and 37, you could record that, but maybe you feel it's a little bit closer to the next one. So you could do a 36.8 milliliters plus or minus 0.5 milliliters in this case. And again, we would have 3 significant figures with the 8 being our estimated digit, our uncertain digit. Any questions on that reading there? That's actually what they got. What do you know? All right. Now, this piece of equipment is known as a burette, and we do use a burette a lot in chemistry. Now, a burette is used in a lot of experiments, especially ones that are known as titrations. And titrations, we use burettes, and they're a little bit different in terms of how we read it. So the burette will empty out from the bottom. You will actually fill it from the top. So you fill it from the top, it comes out the bottom. This is what is known as the stopcock there. That is what turns it on and off. It's like a little turner thing. I'll turn it on and off. Now, what happens on a burette is actually the volume increases as you go down. So when you fill it all the way to the top, it is at 0, basically. And then it goes, as you start emptying out liquid this way, the liquid starts to drop. So if you find yourself like liquid-wise in this area, that is actually 1 point something, not 2 point something. So again, it's increasing as you go down, and your measurement would be like 1 point something rather than 2 point something. By the way, a very common mistake that people make with a burette is they fill it to the top and they go, the entire thing on the very bottom says 50, and they record 50 when they fill it to the top. So you always want to record the exact number where the liquid is on the scale. So if we were to look at this scale, this is 28 and this is 29. And that means that our large markings in this case is 1 milliliter, not 10. And if we look at the markings here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between the large markings. So again, if we divide this by 10, our small markings in this case is going to be 0.1 milliliters. Now, again, if I'm confident on that 0.1 milliliters, I could divide this by 2, and now I got plus or minus 0.05 milliliters. That means when I take a proper reading here, how far should I take it to? How many decimal places? 2 decimal places, right? Again, that's basically what that's telling us. So remember, though, again, it's increasing as you go down. So if our liquid is in this area, it is 28 point something, not 29. So this is 28 point something. So we'll go 28 point, that would be 28.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Between the 0.8 and 0.9, so that's going to be 28.8. Again, you want to take it out of the mix and maybe report it as a 5 milliliters. 0.05 milliliters, 2 decimal places. We're in business, yes. Any questions on that? By the way, that would have how many significant figures that measurement? It would have 4, yeah. Again, the estimated digit there, the 5. Any questions on that there? All right, it's a good place to lay up. We don't